Okay, so welcome everyone in Darmstadt and welcome everyone online for this second lecture accompanying this year's internet seminar on harmonic analysis techniques for elliptic operators. And so this week is the first time that I'm doing the lecture. So once again, you've seen me as a guest star in the last lecture just at the beginning, but I quickly recall that my name is Moritz and I'm going to talk about sectorial operators and sesquilinear forms in the following two lectures. Okay, so the idea will be that we will be talking about a certain class of operators that will be extremely important, and our main example that we're going to work with in the later lectures. And these operators are called sectorial operators because of some geometric restriction on their spectrum and a corresponding bound for the resolvent outside of the spectrum. And then in the first lecture we're going to just introduce this class, see the interplay between the spectrum, the resolvent bounds and the operator, and then we do some brief recap on linear algebra, mainly talking about sesquilinear forms. This is the plan for today, and then on Wednesday, second part of the lectures, I'm going to merge these two things together and I'm going to use sesquilinear forms to define prototypical examples of sectorial operators. Okay, so that's the plan, and so the entire lecture is called Sectorial Operators and Sesquilinear Forms. Okay. Okay, and of course, as always, and same comments as in Robert's lecture, if there's anything unclear, just stop me, ask, and I'm going to help you out. Okay, so we're going to talk about this, sectorial operators and sesquilinear forms, and throughout the entire lecture, I will use the symbol capital H to denote a complex Hilbert space. Alrighty, and so just let us get straight into the matter and start with a central definition telling us what a sectorial operator is. All right. Definition comes in three parts. The first part is to introduce sectors in the complex plane. Okay, so maybe I'm doing a drawing over here. Okay, so this thing here, this will be our complex plane, real and imaginary axis. This is C, and then I'm going to form sectors in the complex plane. Let me draw them in yellow maybe, by taking an opening angle, usually called phi. The sector is symmetric around the real axis, and then this open set I'm going to call S phi, S for sector. And of course, now I measure angle, so angle 0 is over here, angle pi goes over around there, and so these sectors are defined for angles strictly between 0 and pi. Okay, so in formulas, S phi is the set of all complex numbers different to 0, such that their argument in absolute value is less than phi. And this guy I'm going to call the open sector of angle phi. Sometimes it will be just useful to have the sector of opening angle 0. This is going to be, by definition, the open interval from 1 to infinity. So it's the positive real axis without 0. Okay. And now I'm going to call a linear operator, okay, a linear operator L in H. I'm going to call it sectorial of angle phi if two things happen. Okay. First thing is I want the spectrum of the operator to be a subset of the closure of the sector of angle phi. Okay, so that means that the spectrum drawn in red here is some subset of this sector. Okay, and it can go into zero, and it can also spread all the way up to infinity within the sector. Okay, let me draw the usual smiling spectrum over here. Okay, so this set here, this is the spectrum of the operator. Okay, we're going to see a lot of spectra of operators from lecture 5 onwards. There's going to be a lot of drawings over here. Now I drew a smiling face for here. If you want to do some advertising, I mean, I'm open to all sorts of deals that do not contradict the TU Darmstadt's corporate restrictions. So if you want to place your favorite ad here, just get in contact with me and I can see what I can do for you. Because it's a long-standing ad, because, you know, this spectrum is going to be on the board for the entire lecture until I clean blackboards for the first time. And you see there's enormous amount of blackboards here. So, I mean, rarely you have this good of advertising time in a lecture with 300 participants online. Okay. I need to think what serious stuff I want to tell you. Okay, so the first restriction of a sectorial operator is that the spectrum is trapped inside of this closed sector of angle phi. And then the second thing is that if you draw a slightly larger sector, okay, let's draw in orange a slightly larger sector, the angle of which is going to be psi, then what I want is that whenever lambda sits out here, then lambda is going to be in the resolvent set. That's not enough for me. I want to have a growth condition on the norm of the resolvent. And so what I want at these points is that the resolvent in norm is bounded by a constant that only depends on the opening angle of the larger sector divided by lambda. Okay. So that's what I want, and I'm going to write it down here. And I want this for every sector larger than the sector of angle phi that I chose before. So I want, in addition, that whenever psi is going to be between phi and pi, then I want a constant to exist with the property that it controls the growth of the resolvent in operator norm as I drew it on the board. Okay? And this should hold for all lambda in the complex plane without the closure of this larger sector. So I place myself outside a slightly larger sector. Okay. And then, you know, this picture can be true for different choices of angles, and I'm going to call the smallest angle phi that is trapping the spectrum and makes this resolvent bound works. I'm going to call this the sectoriality angle of my operator. Okay, so if L is sectorial, then phi L to be the inf of all angles phi that make the previous things work, this is called sectoriality angle. Is called sectoriality angle of L. Okay. That's a definition. Now, one immediate remark that I can make is you see that these operators have non-empty resolvent sets. So, but what you learned in the last lectures, these operators are automatically closed. What is going to be surprising. And the main topic of today's lecture is the following. So it's remarkable that the two ingredients that we put in the definition, namely location of the spectrum and resolvent bound, that these two things together imply a lot. All right. In particular, I'm going to prove in a couple of minutes to you that these two things together already imply that the domain of the operator is dense. So if you see these kind of things for the first time, this might be surprising, because how can these kind of things imply anything on the operator? Please, there's a question. Yes, it's the inf over all phi that make the first, the B part of the proposition correct. Or in other words, it's the inf, that was the question from the audience, what is the inf, what is phi? Phi is any angle such that L is sectorial of angle phi. And then I take the inf over all these guys, that's the sectoriality angle. Okay. So how do we get there? I'm going to put on the side. Can I use the sideboard, or is that posing a problem? Okay, so I'm going to put on the sideboard before I really go to the heart of the matter and show you how I get a lot of information squeezed out from the properties of a sectorial operator. I'm going to recall a short lemma for you. You probably know from functional analysis, but it's always good to have simple proofs in the Hilbert space setting that we're using here. So the lemma says the following: if K is a closed subspace, and I have a sequence in K that converges weakly, okay, so Uj, a sequence in K, such that Uj converges weakly as j goes to infinity to some u, then what can I say? I thought the cameraman was answering the question for us. No? I mean, the thing is that K is a closed subspace, but this convergence is not with respect to norm, it's just a weak convergence, but nonetheless I can infer that the limit will stay inside of K. In other words, these closed subspaces, they're also closed with respect to weak convergence instead of strong convergence. Okay. Proof, how does it go? Well, you have a closed subspace, so in particular closed convex subset of a Hilbert space, so you know that there is an orthogonal projection. Okay, so P in this case is a linear operator, P and L of H. I'm going to call this the orthogonal projection onto K. Okay? And because K is a subspace, this is a linear operator. It's a bounded one. Okay, now I take any V in my Hilbert space, and I'm trying to prove that the limit belongs to K by showing that it is invariant under the projection. Right? So I do this by testing. Okay, so the overall goal will be to show that this guy over here hopefully is going to turn out to be our U. Okay, so I want this guy to be U. And I'm going some testing way. I'm skipping the indication of H. So the angular brackets always just refer to the inner product on H because it's the only Hilbert space on the table for the moment. Okay, and so in a first step, I'm going to take the P to the other side, write P star VU, because now this is some Hilbert space element. At this point I can invest the weak convergence of the sequence and recover this U as the limit of all these UJs. Now I can throw the projection back, but once the projection hits the UJ, you have to tell me what I have to do. So now what can I say at this point? What happens if I project UJ? Come on, guys. It's itself because it's in K, right? So at this point I can eliminate the P from the equation. Then I use the weak convergence of the UJ again, and I get that this is VU. Okay? And now I'm comparing just start and end of my equality. So against any Hilbert space element V, P of U gives the same test result as U itself. So this, together with this, tells us that PU is equal to U and hence NK. Okay, and the proof is complete. All right. So now let's see how we can use this lemma to prove serious stuff. So this is 2.4 proposition. It's going to be our main entertainment for today. So let L be a sectorial operator in H. And now I'm going to put a list of properties down that just follow from the location of the spectrum and the accompanying resolvent bound, and we're going to prove them one by the other. Okay. The first thing is I want to look at the operators 1 plus TL. They turn out to be invertible, and I can show you what happens with this family of operators in the sense of strong convergence when T goes to infinity. Okay, if this L would be not an operator but just a number, I would be calculating 1 over TL. So if L is a non-zero number, this goes to 0. And the same is true here. Well, at least for all U in the range of the operator closed. As a second step, we are going to use this first property, innocent as it looks, to prove that there is a decomposition of the underlying Hilbert space that is introduced by the operator L. Namely, H is the topological sum of the kernel and the closure of the range of L. Okay? It's a topological, in general, not an orthogonal sum. In fact, in the previous lecture you've seen that the orthogonal complement of the kernel of L would be rather the closure of the range of L star. But nonetheless we have this orthogonal, this topological decomposition. Okay? Topological decomposition means it's a direct sum and there's a bounded linear projection onto either of the parts of the sum. Okay, then part C is the surprising result that sectoriality implies that the operator is densely defined automatically. And in part D, we are going to look at families like this. But we're looking at the limit as t approaches 0 from above. And once again, if you think of L just a bounded operator or a number, and you can make a guess what should come out here. This should be an approximation of the identity, right? Because this thing here should go to 1. And this is exactly true. And in this case, this strong convergence holds for every element in the Hilbert space. Now these things talk about kernel, range, and domain of the operator L. You can somehow bootstrap these arguments and also talk about the domains, ranges, and so on of higher powers of L. This is something that's going to be an exercise for you. But I'm going to write down the statement here. So every natural number k in n, in analogy with part C, you also have that the domain of L to the k is dense. You can also look at the domain of L to the k intersected with the range of L to the k, and you take the closure of this. Now with this construction, you're never going to make it out of the range of L, or more precisely its closure. The statement is that the closure of this smaller space is indeed the same as the closure of the range of L. And then thirdly, and this is completely mysterious why I'm using it at this point, you have to wait another 3 lectures until you will understand why I insist on this point. But this space here, this can also be written as the range of a particular operator, namely L to the k, 1 plus L to the minus 2k. Okay. Just take it as a piece of information I'm throwing at you. It's going to be extremely useful later on. Okay. All these parts here, this is going to be an exercise for you. And I'm going to show you the techniques that are needed to solve this exercise by proving A, B, C, D. Okay. Before I head into the proof of this, questions? You clearly expected all these properties? Maybe not. I mean, I found them surprising when I saw them first time. I mean, the strong convergence, somehow I have an intuition for it, why it's true, but that these things imply that the domain is dense was kind of a surprise to me when I saw it the first time. Yes, please. Yeah. Okay, so a question from the audience is, why do we even know that 1 plus TL is invertible? It's going to be part of the proof to convince you that this is true. Doesn't work for every operator, but we're working with a sectorial operator, which will change everything. Okay. Probably start with a proof on the big blackboard. And I'm going to put a reminder for you on the side. In the proof, I'm using some sort of special 2 epsilon argument from time to time. And I'm always referring to this blackboard when I need it. It's nothing big. It's a thing that you've seen hundreds of times before. Suppose that Tj is a bounded sequence of bounded operators. Okay. In other words, this family Tj of bounded linear operators is uniformly bounded. And suppose also that there is a subset U in your Hilbert space H with a property that these linear operators converge strongly to 0 whenever you apply them to an element in U. Okay? Suppose Tj of U goes strongly to 0 for all U in U. When you have this, then you can use the fact that these operators are uniformly bounded and that elements from the closure of U can be approximated by elements from U by definition to do a 2 epsilon argument and conclude that this strong convergence here, this thing also remains true when U is in the closure of U. Okay? Then this remains true for all U in the closure of U. I guess you've seen these kinds of arguments before. And if not, convince yourself, as we put in a footnote in the lecture notes, convince yourself that this is a 2 epsilon argument. All right. Split the board and get started. Of course, I have to start talking about 1 plus TL to the minus 1. Now, what I'm doing is take this operator 1 plus TL, and I'm going to factorize by T. If I factorize by T, this is going to be T to the minus 1 plus L inverse, and the factorized T, because of the minus 1, will also pop out as a T to the minus 1. Okay? And then you see that indeed these operators are bounded. They're even uniformly bounded with respect to positive T, because this is just the resolvent bound for L at resolvent parameter lambda is equal to minus T to the minus 1. Okay, now I'm going to use this weapon I found over here incidentally to show you that these operators, they are uniformly bounded with respect to T because they translate to the resolvent bounds that you have on the negative real axis. And these lambdas on the negative real axis, they're always part of the resolvent set, and lambda times resolvent is uniformly controlled. So indeed, these operators are well defined, and they are a uniformly bounded family of bounded operators. Does that answer your question? Wonderful. Okay, so I can say that this family is uniformly bounded with respect to T positive. You tell me if I'm using too many abbreviations, you stop me. It's kind of my style to try to use blackboard space very efficiently. Okay, so uniformly bounded with respect to positive T. So why do I say that? I say that because I have to prove a strong convergence over there for every U in the closure of the range. But because this family is uniformly bounded, it's okay to only check it for U in the range. Then the extension to the closure is for free. Okay, so I say that it's enough to look at elements u that can be written as L of v in the range of L is enough. Okay, so v is an element of the domain of L, and that's it. Okay. So why is this useful? Let's see. So 1 plus TL to the minus 1 applied to U then is the same as 1 plus TL to the minus 1 applied to L of V. And now I have to do some plus and minus magic. Okay, so the first thing is this L would better go with a T, so let me put a T here, and let me compensate by putting a T to the minus 1 over there. Okay, and then at this point, if I just look at this part, I do plus and minus, and then I can sort of simplify with a resolvent. So I claim that this is the same as T to the minus 1. If I add a V to this element, then the resolvent will simplify and I just get the V back. And then I do minus 1. Well, then instead of TL, I'm going to have minus 1. So I actually have to subtract the resolvent. Agreed? Well, and then it's not a mystery anymore what's happening in my statement, because these guys, they're uniformly bounded with respect to T. This guy doesn't change, and this is the same things that we've seen before. Okay, so this is in norm controlled by some constant times the norm of V. In particular is independent of T. So as I shoot T all the way to infinity, this will remain bounded while this guy goes to 0. So clearly in the limit as T goes to infinity, this will go to 0. And then I checked A. Okay? So now let me check B. B says that the kernel and the range form a topological decomposition that forms the full Hilbert space H. It will turn out that this is kind of the hardest task that we have to do together. So let's go step by step. In the first step, I'm trying to convince you that at least the sum of these two spaces is a direct one. Okay? In other words, the intersection of the two guys, kernel and range, should be trivial. So let's assume that U is in the kernel of L and also in the closure of the range of L. Okay. I want to prove that U is equal to 0. There's not much I can do at this point. There's only two things I can do. I have to use resolvent bounds in one way or the other, because I have to use that the operator is sectorial. And if the organizers or the virtual lectures have been clever in writing down this statement, that maybe part A is going to be important in proving part B. Okay, so I do brute force approach. I try to introduce what I am given in part A. So because U, as a member of the kernel, is in particular in the domain of the operator, I can write U as 1 plus TL inverse applied to 1 plus TL of U. Sure, nothing happened. But now when I start expanding these things, then from expanding the first guys, I'm getting 1 plus TL to the minus 1 applied to U. And then from expanding the other guy, I'm noticing that first of all, before doing anything else, I'm going to apply the operator L to U. And because U is in the kernel, that gives me 0. And then I don't have to care about what I get next. Okay, so it's already done here, the equality. But now you see, U is equal to this for every t. So if I let t tend to infinity, then because U is also in the closure of the range, I can use the A part to conclude that this goes to 0. So the constant sequence U goes to 0, meaning that U is equal to 0. Okay? Okay, so the sum is direct. That's good news. So now I want to show you why these considerations that I did so far give me a candidate for the projection. A candidate for the projection onto the kernel. Okay? And so let me call uj the element 1 plus jl to this minus 1 applied to some u. Okay? So this u is some element of the Hilbert space. Now let's have a look about what happens with these guys. So we know two things. First of all, we know that when U would be in the kernel of L, okay, skipping that. When U would be in the kernel of L, then we did the computation over there. It follows that uj is equal to U. Okay, so clearly as j goes to infinity, this goes to U. On the other hand, if U would be in the closure of the range of L, then the A part tells me that uj, as j goes to infinity, goes to 0. So what's the conclusion from this? So once we have shown that the kernel of L plus the range of L spans all of H, then it follows that this limit exists for every element in H, and that the limit of these UJs is precisely the projection onto the kernel, because it does precisely what it should do. Okay. So once we know that, then P of U, defined as the limit as j goes to infinity of 1 plus jl to the minus 1 of U, this thing here is the projection onto the kernel that annihilates the closure of the range. Okay? And moreover, once we have shown that this spans all of H, this would be strong limit of a uniformly bounded family of linear operators. So this limiting guy would be a linear operator on H, bounded linear operator, and so therefore the decomposition will become topological in virtue of the projection H. Projection P, sorry. So decomposition is topological. Right? That's the conclusion of these considerations. Once we know that the sum spans all of H, we know what the projection is, and the projection will be bounded, and then it's all fine. The problem is just that we have to prove that this sum spans all of H. Okay? And now, there's a funny twist in this argument, because somehow we're also able to use these uj guys to prove that the sum spans all of H, which seems like we're somehow pulling ourselves out by our own bootstraps. I'm going to show you that exactly this happens, okay? So I'm going to use the UJs also to prove that the sum spans H. Okay, so sum spans H. How am I going to do that? You have to help me. I mean, my main issue here is, what's my main issue actually? My main issue seems to be that I do not know that the uj converge for every u. I just know it separately on the range, on the closure of the range and the kernel, but I do not know how much information that gives me because I do not know what these two sets span as a subspace of H. Right, so I could have said differently, I would have to prove that the uj converge for every u, which I do not know. But I do know that the uj in H, they are bounded for every u. Okay? So let u in H. uj is a bounded sequence in the Hilbert space, so I don't know that it converges. I don't know it has a convergent subsequence, but I know that it has a weakly convergent subsequence. Okay? So pick a subsequence ujk is a subsequence such that ujk, as k goes to infinity, converges weakly to some element that I'm going to call v. This does work. Up to passing to subsequence, at least I can assume it's convergent in the weak sense. Okay. I'm going to continue here. Now the next thing is, I want to put this sequence in relation with the operator. Okay, so let's see what happens when I compute L of ujk. I mean, these ujk are in the domain of the operator by construction as resolvents. Okay, so let me write down what that is. This is L plus 1 plus jk L to the minus 1 applied to u. Okay, now I have to do some sort of similar trick as before. I'm introducing by brute force a jk and I'm compensating by a 1 over jk. And then these two guys here I'm going to put together and I'm adding plus and minus 1. If I add a plus 1, then I'm left with 1 over jk times u, and if I do a minus 1, then I'm doing minus 1 over jk 1 plus jk L to the minus 1 of u. if you look at this more closely, then you see this is exactly 1 over jk times u minus ujk. Because this was the definition of jk. Now this is constant, this is a bounded sequence. I'm dividing by jk, goes to infinity. In other words, this here goes, as k goes to infinity, strongly to 0. Okay. Now, let's put the two things together. I can look at both of my auxiliary results simultaneously by merging them into a sequence in the product space h times h. Okay? And now in the limit, as k goes to infinity, I have weak convergence of this guy towards v, and I have strong convergence, hence weak convergence of this guy towards 0. So this guy goes weakly to v, 0 in the product space. But I know that the elements of my sequence, they are contained in L. And L is closed. So it means, what does it mean? Now I use the lemma over there. I have a sequence in L, which is the same as L bar, converges weakly to this element. It follows from number, is it 2.3? It follows that v, naught remains in L. Now that means that v is in the kernel. Because it means that L of v is equal to 0. So v is in the kernel. Great. So I have at least managed to put an arbitrary element from my Hilbert space in a more or less constructive way in relation to something from the kernel. Now, let me have a look on what the rest does. Okay? Moreover, let me look at u minus ujk. Now, in the limit, as k goes to infinity, I can say that this guy goes weakly to u minus v. All right? Now, what do I want to know about this element? What is it that I'm so desperately searching for? Please. If it is u, no. I want to write u as a union, remember, as a sum. Element in the kernel and in the range. Closure of the range. And I know that this v guy is in the kernel. I want to know if this guy is in the closure of the range of L. Then I would be done. Now, is it so? Well, u minus ujk, I can go back to here. Okay, I gave this a number. This was equation 2.1, I should call it. By 2.1, I can say that u minus ujk is, I put this to the other side, jk times L ujk. So this is in the range of L, so it's also in the closure of the range. It converges weakly to this guy, so it follows once again from 2.3 that u minus v is in the closure of the range of L. Alright? And so I can conclude that u is equal to u plus v minus u, plus u minus v, u is equal to, v plus u minus v is in the kernel of L plus the closure of the range of L. And so I showed that the sum spans all of H, and hence the decomposition is direct, spans all of H, is topological by our considerations before, so we proved this B part. Okay, I think that's a very good moment for doing a break of round about 8 minutes. I'm going to resume at 12:40 for the locals, and for the others doesn't make a difference. Alright, so let's resume. I left two things for you. I left this guy, because we're going to need it in a second, and I left the overall plan for this proposition. So A and B are settled. Now I want to jump right into part number C. Okay, so I'm continuing here. So we're inside of this proof. And now the next thing that I have to show you is that the domain of L is dense. Okay, now there's a trick. I claim that 1 plus L to the minus 1 is sectorial, okay? And this is left as an exercise for you. But it is kind of plausible that this should be true if you're not following the resolvent bounds, but just the location of the spectrum. But if I go from L to 1 plus L, this means I'm shifting the spectrum to the right. And shifting to the right is an operation that preserves the sector of angle phi. And then if I go to the inverse, there's some sort of spectral mapping theorem tells you that I have to compute the inverse separately for every element in the spectrum by switching from Z to C inverse, so 1 over Z, is yet another operation that preserves this sector. If you write things in polar coordinates, it's like r to the e exponential I phi. You take the inverse, changes the radius, puts a different sign on the angle, but stays inside the sector. Okay, and you're going to verify it rigorously as part of the exercises. It's also true that this operator is injective, because minus 1 is in the resolvent set of L. Right, so this is going to be an injective sectorial operator. Now I can use the B part for this new operator. Let's have a look at the B part. Well, the B part gives a topological decomposition. In particular, the operator is injective, means that the kernel is trivial. Now, how can this ever happen? Well, according to B, for a sectorial operator, this happens if and only if the range of the operator is dense. So now, because this sectorial operator is injective, I know that the range of 1 plus L to the minus 1 is dense. So this space is everything. But the range of 1 plus L to the minus 1 is nothing but the domain of 1 plus L. And the domain of 1 plus L is the same as the domain of L, because this guy is bounded. Okay, so now you compare what I've shown you. Well, H is the closure of the domain of L, so that's already it. Sweet and easy. D is also going to be sweet and easy, but I need you again to tell me how I should start. So now I want to look at these 1 plus TL minus 1 guys. I want to prove strong convergence everywhere on H to U. Now, I want to use that lemma that suffices to do that on a dense subset. And now the dense subset, what should I pick? What can I pick? What could be helpful? Please. Yes, the domain of L is the suggestion, and that's exactly what I'm going to do. So U in domain of L would be enough to prove the statement 4. Okay, and now what do I do if U is in the domain of L? Well, I'm doing the good old trick once again. Okay. And now I'm separating the two elements. Gives me 1 plus TL to the minus 1. This is the guy that should converge to U. So in other words, what comes out of the other calculation should be something that is bounded and goes to 0. Okay, should be an error term. So how do I manage the other terms? Well, I'm going to put the t in front. Then I'm doing 1 plus TL to the minus 1 applied to L of U. And then by our standard argument, this here is bounded with respect to t. But now t is a factor and goes to 0, so the whole thing goes to 0. Okay. So as t approaches 0, this goes to 0. And so I proved that this guy has to tend to U, which is exactly what I want. Okay, so proof achieved. So now I think it's time for an example, and what I want to do is I want to pick Robert's favorite example from last week, namely multiplication operator, and I want to discuss when this guy becomes sectorial. Okay, so the question in this example is, when is m of m sectorial of angle phi? Okay, say phi in 0 pi. Wow. Okay. So one thing you can already answer, namely you can give a necessary condition from using definition of sectorial operators plus what you've seen last week. Namely, you have seen that the essential range of M was the same as the spectrum of the multiplication operator, and so it is necessary that this essential range shall be a subset of the closure of the sector of angle phi. That's necessary. So it says that, seems to say it's necessary that the multiplier function m has range in the sector for the multiplication operator to be sectorial. Well, it's beginning to look tautologically, which is a good thing at this point. Now I claim this is also sufficient. Okay, so what is missing is that the geometric location of the spectrum alone, in case of these very special multiplication operators, already entails the resolvent bound that you need for general sectorial operators. Just side remark before I jump into the proof. If this would be true, it would show once again that the restriction we're putting here is a very natural one. Okay? So, let's see. Why is this sufficient? Well, okay. I have to do as the definition that I erased tells me, so I take an angle psi between phi and pi. And you can always look at this picture. I'm going to get to the picture in a second to do the work with you. And then I'm taking lambda outside of the closure of the larger sector. Now, picture is, think of it exactly as it is here. So lambda is here. I'm outside of the orange sector and the spectrum. The central range is in the yellow sector. So I need the resolvent bound. All right. So I need to compute the operator norm of the resolvent of M of M. But outside of the central range, you have already clarified what the resolvent is in this case. Right? Once again, 116 tells you that the resolvent is the multiplication operator with a function lambda minus m to the minus 1. Okay. And then this is a multiplication operator and I want to bound its norm. Well, you had this discussion with Robert. When is a multiplication operator bounded? And I think in 1.9 he told you this happens precisely when the function down here is bounded, and in this case the norm is precisely the L infinity norm of the function I'm multiplying with. In other words, this is the same as lambda minus m to the minus 1 in L infinity of Rn. Okay? And now here lambda is a number, m is a function that takes values in the closure of this sector. So the L infinity norm of this guy here for sure is bounded by 1 over, first of all, the norm here, and so this is 1 over the distance of lambda to the sector in which m takes its values. And if you would write this out, this m, you can just think of any number in the sector, and then I'm calculating the size of this number. Well, it will not be bigger than this. Okay. Well, now there are a billion ways of doing the elementary geometry that gives you more information about how far is this lambda going to be away from the sector. Right, but if you just look, and I'm not going to do that, you're going to find it in the lecture notes, of course. Let's just focus on why that should be true. Well, what you see is that there seems to be some scaling invariance. Okay, so if lambda is outside of the orange sector, then the distance of lambda to the smaller yellow sector is going to be comparable to the absolute value of lambda. You could calculate it explicitly if you want, using cosines and so on. There's also a more analytical argument in the lecture notes. But I think no matter which argument you use, it's clear that the distance of lambda to this yellow sector will be controlled by a constant that depends on how far the orange and the yellow angle are far from each other, times the absolute value of lambda. Okay, and so I can say that this here is bounded by a constant divided by the absolute value of lambda. You agree? Or you want me to do the geometry? Do it yourself. Sometimes it's fun to do elementary geometry. Do it yourself first and then check how we did it in the lecture notes to save one more line. Okay, and so it says that because of the very special structure of these operators, the resolvent bound is a consequence of the location of the spectrum. And so this condition is not only necessary, but is also sufficient for the multiplication operator to be sectorial of angle phi. Alrighty, questions? So fine? Okay. So, I mean, the elephant in the room is, of course, where do these sectorial operators come from? We have one construction from multiplication operators, but we want to do a lot more than just this. Okay? And so, as I told you in the beginning, there's a construction using sesquilinear forms that will enable us to manufacture sectorial operators and also to link them with partial differential equations in the later lectures. And so in the remainder of today's lecture, I'm just doing the groundwork on sesquilinear forms. It is, in some sense or the other, maybe a reminder on linear algebra for you, but it is worth doing it, introducing some vocabulary that will enable us in the next lecture to construct more interesting sectorial operators. And so in all that is going to come, I'm assuming that there is a subset V of H, and this V is equipped with another norm, not necessarily the H norm, and it's a Hilbert space with respect to this V norm. Okay, and I want the embedding, or inclusion if you want so, of V into H to be dense. Now, the sesquilinear forms, they will act on V, but they will induce operators in H. And that will be important for us. Okay, so 2.7 definition. Okay, so in the following I'm going to work with A defined on V2V valued in C, and this is going to be a sesquilinear form. Okay, and when I talk about sesquilinear forms, in all of the lectures, they're going to be linear in the first component, and they're going to be anti-linear or conjugate linear in the second component. And as a short notation, if I only put one argument in the form, that I mean is the associated quadratic form. Okay. This is a short notation. You might say, why using short notation? Well, if you wait 20 more minutes and you see how many quadratic forms I'm going to put on the board, then you will agree with me that it's a good idea to use this abbreviation. Okay, so this is a quadratic form and this is a sesquilinear form. Okay, and now a sesquilinear form can have a bunch of properties that are needed and useful for us. Okay, so we're having a sesquilinear form as above. And now the sesquilinear form is going to be something if it satisfies something else. Okay, with these properties we're laying the groundwork. If I want to link sesquilinear forms with sectorial operators, sooner or later it will not be surprising that I have to talk about the values that the sesquilinear form can take. Okay, so one notation that we're using is we say this form is symmetric if A of uv is the same as A of vu bar. And I say it's bounded if I can bound A of uv in absolute value by some constant times u in the v norm times v in the v norm. If you've seen a course on functional analysis, like Smukram's lemma, you will recall these sorts of notation. You will also recall the notion of coercivity of a form. I say that the sesquilinear form is coercive if there exists a positive constant such that I can bound the real part of u from below by the v norm of u squared. Okay. Now these statements are of course to be read if there's no quantifiers on u and v, then it's going to be all u and v in v. Okay. Now, besides these two things that you might have seen before, there are two notions that will be important for us, because working with coercive sesquilinear forms will be too restrictive for what we're trying to do. And so we say that the sesquilinear form is accretive if the quadratic form only takes values in the right complex half plane. In other words, if the real part of A of u is always non-negative. And then, leading us to the topic of the Internet seminar for the first time, I'm going to say the sesquilinear form is elliptic if it's something like coercivity, but I can compensate by adding a little bit of H norm to the left-hand side. Okay, in other words, I assume that there exist two constants, positive, omega and kappa, such that the real part of A of u is controlled from below by kappa times the v norm squared. This would be coercivity, but here I allow myself to work only in the setting where I can add a little bit of H norm squared to the left-hand side to make the form coercive. Okay, so this perspective ellipticity means coercivity of a slightly shifted form will be important in the next section. And then you're going to fully appreciate why it's a good notion for what we're trying to do here. Okay, for the moment, this is vocabulary. I should also remind you of some things that you've seen before. First of all, when you look at the quadratic form, you might wonder, why am I posing all these restrictions only on the quadratic form? Is it not true that I lose too much information when I switch from sesquilinear forms to quadratic forms? It's a natural question. And the answer is no. There is the polarization identity, that allows you to recover the sesquilinear form from the quadratic form. Okay, and we're going to see it in action in the next statement. So how do I write the sesquilinear form in terms of the quadratic form? There's going to be a 1 over 4 in the complex setting, and then it's going to be A of u plus v minus A of u minus v plus I times A of u plus iv minus I of A times u minus iv. I guess you've seen that before. If not, you can expand the right hand side and you're going to see that it gives you back the left hand side. Okay, so, and this is useful because it says recover the form from the quadratic form. In a similar spirit, there's also the parallelogram identity, which tells you that because this quadratic form comes from a sesquilinear form, this identity holds, and it gives you 2 times A of u plus 2 times A of v. It's the same as A of u plus v plus A of u minus v. Also straightforward, expanding the thing gives you precisely that. Okay. Well, why insisting on these things? We need some more information about sesquilinear forms that are not always covered by what you learned in linear algebra, or because linear algebra is so long ago you might have forgotten. So because I'm going to work extensively with sesquilinear forms in the next lecture, I think it's a good warm-up just, to recall and remind ourselves what we can do when we work with a sesquilinear form. So just for fun, let's prove some stuff. Okay, so suppose I have a sesquilinear form, and I want to know when this guy is symmetric. I claim that A is symmetric precisely when the quadratic form only takes real values. Okay, so you can check, somehow you can check symmetry from evaluating the quadratic form in that way. Well, okay. One direction should be easy, because if the form is symmetric, then A of u, which by definition is the form evaluated at u, u, is the same as u, u bar, which is A of u bar. And so A of u always is a number that is equal to its own complex conjugate, which happens if and only if the number is real. All right. That's a no-brainer. How do you do the other one efficiently? Well, let's see. Let's look at A VU and let's write it out. Okay, so A of VU is going to be 1/4 of A V plus U minus A V minus U plus I bar A of V plus IU minus I A of V minus IU. Okay. Now I want to check that the form is symmetric, so I should look at the conjugate of this. And by assumption, the quadratic form only takes real values. In other words, this is real, and if I want to take the complex conjugate, I just have to switch the minus sign here and take a complex conjugate here, and then I have to put a plus sign here and take a complex conjugate here. Okay? And then also, because the form once again takes real values, actually I can forget about the complex conjugate, and it's just this. Right. So now it's a question of writing out the terms correctly. I'm going to do nothing to the first term. Then in the second term, I'm going to put a minus sign out. In the third term, I'm going to put an I as a factor. And in the last term, I'm going to put a minus I as a factor. Okay, you see, I times I gives plus V. Okay, so that should be correct. But then I'm working with a quadratic form. Okay, so the minus sign, it just goes out and doesn't do anything. The I doesn't do anything. The minus I doesn't do anything. So these terms all go away. And when you compare what I wrote down here, I can also shift the order of U and V. Doesn't do anything. You look at these terms, well, this should be precisely what is written here. See, first two terms are the same, then this term shows up over here, and this term shows up over here. In other words, this is the same as A of U comma V. Okay, and so our proof is complete. So it's one example where you see in action how the quadratic form plays back information to the sesquilinear form. So I want to do one more result before I end the lecture. This is going to be Schwarz's inequality. Okay, and Schwarz's inequality is as follows. I assume that A and B these two guys are symmetric sesquilinear forms. And moreover, the form B dominates the absolute value of the form A. Okay? So you have a bound of one of the sesquilinear forms by the other one, and then the statement is that now I can prove something that looks like Cauchy-Schwarz inequality. I can also prove that the sesquilinear form bar A in absolute value is bounded by the quadratic form in the way that you would expect, resembling Cauchy-Schwarz inequality. Okay, so the sesquilinear form is bounded by the product of the two evaluations of the quadratic form B. Okay. How much time do I have? 10 minutes? Is that right? Okay. Let's try to do the proof. To stay acquainted with these sesquilinear forms. Okay. So let's fix elements in the Hilbert space V. And now there's a trick. Okay, the trick that I'm going to do is not necessary. You can also run a longer argument, and you don't need a trick. Okay, but I mean, I'm a dad of two girls. The older one is 3 years old. Okay, so if I can save some time and buy a stupid trick, then no matter which time of the day, I'm willing to take the trick and do it. And so I'm going to do it here. Okay. And now the trick goes as follows. I'm going to pick a rotation in the complex plane such that this complex number A of uv, right? This is a complex number. Now I can use some rotation gamma that will depend on these vectors, of course, such that this guy becomes a real number. Okay. And why is this useful to do that? It's useful because now I can start writing out things. Gamma of A uv, this is the same as A of gamma uv. But because this is a real number, this is also equal to the real part of this number, because this number over here doesn't have an imaginary part. So this is the real part of this. Alright, now this thing here can be spelled out through the polarization identity, but because the forms that I'm looking here are symmetric, the 2.9 tells me that all these quadratic forms, they are real numbers. So if I put 2.8 and 2.9 together, it says that for the real part, I only have to take into account the first two terms of the polarization identity. In other words, this is the same as A of gamma u plus v minus A of gamma u minus v. Agreed? So the trick basically saves me writing two more terms and doing more messes when now taking absolute values. If I take absolute value, the gamma doesn't play a role, so I still bound the absolute value of A of uv by a quarter times the sum of the absolute values of this guy and this guy, but by the assumption I can bound this and introduce b to the equation. In other words, I can say this is b of gamma u plus v plus b of gamma u minus v. Put absolute values on both terms, use the assumption over there, and get this. Now this is some sort of a sitting duck for parallelogram identity. I use the parallelogram identity for the B, and I can play this back to the form that separate u and v. In other words, this gives me a half b of gamma u plus b of v. Okay? Now the gamma is of absolute value 1. I can pull it out of the quadratic form. So this gamma goes away. And now if you compare this with this, we have an additive bound for the sesquilinear form A at the vectors u and v. And the gamma of my little trick has completely disappeared from the end result. In other words, this bound here, now this is valid for all u and v in my Hilbert space V. And so what remains to be done is to use a trick to transform this additive inequality. Additive, I mean, because on the right hand side, the things I want, they do not show up as a product, they show up as a sum. I have to find a trick that transforms the seemingly much weaker additive inequality into the stronger multiplicative one. And the trick uses the fact that this additive bound is valid for all vectors, u and v in the Hilbert space. And there's a rescaling argument that allows me to complete the proof. So let me take positive numbers. S is larger than the square root of b of u, and t is larger than the square root of b of v. And now I'm going to write out a of uv as the following thing. I'm going to introduce s of u, u over s, sorry, so 1 over s, and I'm going to introduce 1 over t in the sesquilinear form, and in order to compensate, I'm just stupidly multiplying by st. No big deal. But this is going to save our lives in these estimates, because now I'm going to use the first part, the additive bound, but I'm using it for this pair of vectors. So this is bounded by st over 2 times b of this guy, and there I can pull out the s, so it gives me b of u over s squared plus b of v over t squared. Okay? The 1 over s out of the quadratic form goes out with a square. Okay, but s is larger than b of u, and t is larger than b of v square root. In other words, this term here is bounded by 2. And so the 2 cancels. You just get st, and you just have to recall what s and t was. Well, s and t were any real numbers larger than this or this. So if this is true for any real numbers s and t with these properties, I can send s to the square root of b of u, and I can send t to the square root of b of v. And this right-hand side, s times t, approaches precisely what I want. Okay? That's the proof of Schwarz's inequality. Okay, I know from my definition, that from my notes, that I should put you one more definition on the board, but I'm going to save that for the next lecture. Yeah. Should I save it for the next lecture? yeah, I'm going to save it for the next lecture. Going to give us a good way of recalling some of the vocabulary before we get started into the more serious stuff. So yeah, thanks for joining me. Do you have any questions on that? Well, if this is not the case, then this is the end of this lecture, and I'm going to see you guys on Wednesday. Thanks.